Hello everybody! Today we're going to talk about section 6.1, which talks about complex numbers. Complex numbers are defined to have the form a plus bi, where a and b are real numbers. So you might be wondering, what is this I that's in this form? And so I is defined to equal the square root of -1. And that means that I squared is equal to -1. So let's do a little exercise just to really understand how the form of complex numbers works. So here, for example 1, it says determine the real and the imaginary part of the complex number. And so the imaginary part here is whatever's in front of the I. So here's the complex number. So the first one is 3i. So notice that, again, my real part is whatever is being added or subtracted to my 3i form. And since there's nothing being added or subtracted to the part that has the I in it, then my real part is just going to be 0. My imaginary part, and again, is whatever's in front of the I. Okay, but whatever real number's in front of the I. And in this case, it's going to be just 3. Just 3. Okay, not the I. The I does not come along. For 4 minus 5i, the real part, again, is whatever doesn't have the I, and that's going to give us 4. That's the real number there. And the imaginary part, again, is the real number in front of the I, which is going to be -5. This one's a little bit tricky here. Okay, and so again, notice that the 2 is dividing that whole complex number up there. So I could rewrite this as 1/2 plus pi over 2i. And so now when I wrote it in this form, the a plus bi form, now we can clearly see what my a is, my real part, and what my imaginary part is. So my real part is 1/2, my imaginary part is pi over 2. All right, so how do we add, subtract, and multiply complex numbers? So it's actually just as intuitive as you would think. You would combine like terms, you would do FOIL method for multiplication. So it's something that is comfortable for you, that we've done before. So for example, when we're adding, let's say the complex number a plus bi and the complex number c plus di, we just combine like terms. And so here, notice again, we have a plus sign in the middle, so nothing's going to change for this. So we have a plus bi plus c plus di. We focus on the like terms. And so we have a plus c plus bi plus di. So we're going to have a plus c plus, and I'm going to factor out that I from both of those, b plus di. So here's my real part. Again, this is my real part, and this is my imaginary part. Okay, so again, you just combine like terms and then factor out the I. So same with the subtraction, but here in the subtraction we have to be a little bit careful because we have to actually distribute that negative. So we have a plus bi minus c minus di, and again combine like terms. So we have a minus c plus bi minus di, which is going to equal to a minus c plus, and we're going to factor out the I, so we get b minus di. So notice how the formula ends up working out. So if you're subtracting two complex numbers, all you have to do is subtract the real part, and then plus subtract the imaginary part, and then just times I. So you don't actually have to go through all of these steps. Again, if you notice what the formula is doing, then you can just jump into the formula. Okay, just subtract the real parts, subtract the imaginary parts, and then add the parts together. FOIL method. Let's try the FOIL method here. And so again, I'm going to multiply a times both of the a times this binomial, and then b times that binomial as well, and combine like terms. So we have a times c plus a times di plus c times bi plus bd, and then I times I is I squared. But don't forget, I squared is defined to be -1. And so this is going to be AC minus BD, because again, I squared is defined to be -1. And then plus AD, I'm going to factor out the I already. This shouldn't be, oh yeah, this is going to be negative. And then plus B, I'm a little lost. Okay, and CBI. Okay, so again, the real parts and the imaginary parts together. So let's actually practice doing this with values. That way we don't have so many variables running around. So let's try example 2. Perform the indicated operations with the complex numbers. All right, and so again, we could just use the outcome that we got from these formulas, or we could just do FOIL and combining like terms. But again, notice how the formulas work as well, if you wanted a shortcut. So A is 6 minus 7i minus 3 minus 4i. So again, there's two methods. You can just do FOIL, combine like terms, you'll get the same answer. You can just use the formula that we ended up getting. Where for part A, that would be subtracting them. So you would just subtract the real parts and then subtract the imaginary parts and then add them together. It's going to give you the same thing. So this is going to equal to my subtracting the real parts. So that would be 6 and 3. And then subtracting the imaginary parts, which is -7 minus 4. And that's a little I. And so it simplifies to 3 minus 3i. And so again, if you didn't want to use the little formula, I'm going to do it just FOIL method, and you'll see that it's the same thing. So this is going to be option 1. And then option 2, we have 6 minus 7i minus 3 plus 4i. Again, if we combine like terms, we get 6 minus 3 and then -7i plus 4i, which is going to be 3 minus 3i. So notice that we got the same thing. So again, it just depends on your personal preference. Okay, so let's try B. And B here, we're going to do FOIL. So we have 3 minus I, 5 minus 2i. And again, we can use the formula or we can just do FOIL, whatever's more comfortable. So here, let's just do FOIL method here. So we have 15 minus 6i minus 5i plus 2i squared. And again, I squared is equal to -1. So let me just write that out. So this is equal to 15 minus 2, and then -6i, -5i gives us -11i. So the final answer here is 13 minus 11i. Okay, so when we multiply these two complex numbers together, we get 13 minus 11i. Now C here, we have a little bit of square roots. So we have the square root of 6 plus I times the square root of 3 times the square root of 6 plus I the square root of 3. Again, there's a power 2, which means we're going to multiply these binomials together. These binomials here together. All right, so the square root of 6 times the square root of 6, that just gives us 6. The square root of 6 times the square root of 3i, that's going to give us the square root of 18i. Right, so just ignore the I for now. Okay, just multiply the square root of 6 times the square root of 3. That's the square root of 18. And then we have the I. And then we have the same inner product here. So you can either have the I in the front or the I in the back when you're having radicals. Normally we have them in the front because again, we don't want to confuse ourselves whether it's inside of the radical or not, because again, it could get lost in the work. And then the last one is going to be I times I, which is just I squared. And then the square root of 3 times the square root of 3 is just 3. So if we clean this up, we get 6 minus 3, because again, negative I squared is negative 1. So 6 minus 3 gives us 3. And then we have the square root of 18i plus the square root of 18i. These are like radicals. So we get 2 square root of 18 times I. We can actually simplify the square root of 18 because we know that the square root of square root of 18 has a perfect square in there. 9 is a perfect square. And so this simplifies to 3 plus 2. And again, this is going to be 3 square root of 2i. And so we multiply the 2 and the 3 and we get 3 plus 6 square root of 2i. So that's going to be my final answer there. And again, you can either do FOIL method or just follow the formula that we have up here. However you want. We got the formulas from actually doing the FOIL method. So hopefully you're comfortable adding, subtracting, and multiplying complex numbers. It's not too different, except we have to remember that I squared is equal to negative 1. Okay, so let's talk about how to simplify powers of I. Okay, because what if you get on the exam I to the 1,000 power? Are you really going to multiply I 1,000 times? I've seen it. Students have actually tried to expand I as many times as I have the power. And trust me, all the times that they do that, they get it wrong because again, it's so easy to just lose track. So you'll see what I mean in a little bit. Okay, so we know that I squared is equal to negative 1. How we're going to do it in this class is we're going to use rules of exponents to, again, make this a little bit of an easier work instead of just like memorizing a bunch of powers of I. So let's just refresh your memory on some of rules of exponents. So we have base A raised to the power x times base A raised to the power y. Because the base is the same, we're going to be able to add the exponents. So we have A, the base stays the same, and we're going to add the exponents. Okay, so this is multiplication. This is not the dot product, even though, again, we just talked about the dot product, so that's kind of confusing, but this is just multiplication. Okay, so when you multiply two numbers that have the same base raised to the power, then we can just add the powers and leave the same base. Now, if we have the base A raised to a power, and then that's being raised to another power, we can multiply the powers together. So A is now x times y. So we're going to be using these rules of exponents to help us simplify powers of I. So again, let's try example 3. We have problem A that says simplify I to the 35th power. Again, we don't want to multiply, we don't want to write out I times I times I times I times I 35 times. It's not efficient at all. Okay, so we're going to use rules of exponents here. And so here our answers, so here I'm giving you guys a little hint that our answer is going to be I, negative I, 1, or negative 1. If our answer is not one of these four, then we didn't do it correctly or we haven't finished simplifying. Okay. So all I want us to use is the fact that I squared is equal to negative 1. Okay. So somehow using rules of exponents and using this property, we're going to rewrite I to the 35th power. So here we could use rule number 1 or rule number 2. Let's see what we can use. I could split I to the 35th power as I times I to the 34th power. I could do that. Because again, since the base is the same, the base is I here, then I can sum up the powers. So I would get back I to the 35th power. All right, but I'm still left with I to the 34th power. But I do know that 34 is divisible by 2, so I can use property number 2 here. So I could rewrite I to the 34 power as I to the second power raised to the 17th power, because we know that 2 times 17 is equal to 34. And so again, if I go backwards, I'm back to I-35. So I haven't done anything wrong here. All I use is rules of exponents to rewrite I to the 35th power. Okay, so again, this is I just used rule number 2 here that I wrote down. Okay, well, let's clean this up a little bit. We have I, and remember, we know that I squared is equal to -1. So we have -1 raised to the 17th power. A negative number, when it's raised to an odd power, is going to remain negative. So for example, if you have -1 to the third power, so let me write that down. If you have -1 to the third power, that's the same thing as -1 times -1 times -1, which is still -1. But the moment that you raise it to an even power, let's say 2, we have -1 times -1. Negative times a negative becomes a positive, which is just going to be 1. So whenever we have a number raised to a odd power, it keeps it negative. Okay, in this case, because it's -1, because it's actually 1, it's still going to be -1. And so it's going to equal to I times -1, which is just going to be -I. And that was one of the options that we could have. So I to the 35th power, that's the same thing as just -I. Pretty cool stuff, I hope. Let's try B. So simplify I to the 24th power. Again, we don't want to expand this out and just see what we get. We're going to want to use the rules of exponents and the fact that I squared is equal to -1. Well, here we already can see that 24 is divisible by 2. So we could just jump into rule number 2 for rules of exponents. This is just equal to I to the second power all raised to the 12th power. Because again, 2 times 12 is 24. So we still have the previous thing. And we know that I squared is equal to -1. And so -1 to the 12th power, again, 12 is an even number. And so we're going to end up getting a positive number. So -1 to the 12th power is just going to be 1. And so again, that's one of the options here. So use the rules of exponents to kind of help you be more efficient with these kinds of problems. So let's move on and talk about the complex conjugate. So the conjugate of a complex number. All right. So if a and b are real numbers, then the product of a plus bi and its conjugate a minus bi. So they're already telling you that the conjugate of a plus bi is a minus bi, is the real number a squared plus b squared. And so if they're saying if you multiply a plus bi and its conjugate, you actually don't end up you end up with a number that doesn't have I in it. Okay, so we're going to have a squared plus just b squared. Okay, so we end up with just a real number. And so let me just make sure to highlight here that the conjugate of a plus bi is a minus bi. So we change the power of the real number that is in front of the I. We change the sign. We change the sign of the real number that's in front of the I. So if my real number was 5, then it's going to be -5. So here, let me just give some examples. I think I said something that was weird. So let's say that I have 5 plus 3i, then its conjugate is going to be 5 minus 3i. So we're going to change the sign of the real number that is in front of the I. Hopefully I said that the first time, because sometimes I feel like I, I, I say something, but I write something else down. Okay, so actually this is problem A. So let's do another one. So if we have 5, I keep using 5 because 5 is my favorite number. But let's say -1 minus I. Okay, the conjugate of this, and again, the only thing that's changing, the only sign that's changing is the sign of the real number in front of the I. So we don't mess with the real part, just the imaginary part. And so we're going to have the conjugate here is going to be -1 plus I. So hopefully that helped clarify what I was saying earlier. Okay, now if we multiply these two together, the real number and its conjugate, we actually end up with a number that doesn't have an imaginary part. And so that's what this statement here is saying. Okay, and again, that works well, especially when we want to rationalize the denominator of a complex number. We know that if we multiply it by its conjugate, we're going to get rid of, the imaginary part, or in this case, or the when we multiply by its conjugate, we end up eliminating the radicals. So let's try these two examples. It says write each quotient in the form a plus bi. Okay, so it's definitely not in that form. So I'm going to start with a. So 4 over 1 plus I. Okay, so it's definitely not in that a plus bi form. Okay, we cannot separate these two fractions right now. But if we just had one single number in the denominator, then we could split up the fraction. Well, why don't we multiply by the conjugate? If we multiply by the conjugate, we know that we're going to end up with just one single number in the denominator. We won't have to deal with any imaginary parts. So I'm going to multiply by the complex number top and bottom again, because we have to keep we have to still maintain the original formula or the original expression here. So I'm going to multiply by the conjugate, which is going to be 1 minus I. So we're going to do FOIL. This is going to be 4 minus 4i all over. And again, you can either use the formula here, or you can do FOIL or distributive property in the denominator. I'm just going to use the formula here. So it tells me that we're going to end up with a squared plus b squared. And so my a here is 1, so I'm going to have 1 squared is just 1. And my b is 1 as well. Okay, my b is just 1. And so 1 squared is just going to be 1. So 1 squared plus 1. Okay, so we get 4 minus 4i all over 2. So now, because we have just one single number in the denominator, we can actually split this up into two different fractions. So we have 4 over 2 minus 4 over 2i. Let's simplify that a little bit. We get 2 plus 2i. Let's try b, because b looks a little bit more complicated. There's a lot of square roots in the way. So we have the square root of 2, the square root of 3 minus I square root of 2 all over the square root of 2 plus I square root of 3. Okay, so we want to divide these two together. The way that we divide these two and have it in the form a plus bi is, again, by having just one single number in the denominator. And what's going to help us get that is actually multiplying by the conjugate. So I'm going to multiply top and bottom by the conjugate. So we have the square root of 2 minus I square root of 3 times the square root of 2 minus I square root of 3. I'm going to add parentheses here because, again, we have binomials, so we want to make sure that we multiply every single term here. So let's do this. We have the square root of 6 minus I times 3, because the square root of 3 times the square root of 3 is just 3. And then minus I times 2, which is going to be 2i, And then at the end, we get plus I squared times the square root of 6 all over. And again, the denominator is going to be just a squared plus b squared. My a is the square root of 2. My b is the square root of 3. So we just have the square root of 2 squared plus the square root of 3 squared. So let me simplify this a little bit. So here, let me show a little bit more of my work. Let me clean this up. So I have the square root of 6 minus 3i minus 2i. And again, I squared is just negative 1. So negative 1 times the square root of 6. And then down here, we get square root of 2 to the second power. That's just going to be 2. Square root of 3 times to the second power. That's just going to be 3. And so let's clean this up. So square root of 6, they end up actually going to 0 here. And we get negative 5i all over 5. We simplify that, we actually just get negative I. And if we want to write it in that a plus bi form, then we could just write it as 0 minus I. Okay, because again, my a is going to be 0, my b is negative 1. So this is just writing it in that a plus bi form, just in case we want it in that form. So this is going to be in a plus bi form. All right, smiley. Okay, so last topic is going to be, all right, how do we simplify when we have a negative in the square root? And so this definition is telling us that for any positive real number b, if we have the square root of negative b, that's equal to the same thing as I squared of b. So why is that true? So if we have the square root of negative b, well that looks like a terrible b. That's equal to the square root of negative 1 times b. I hope you guys all agree. And by rules of radicals, it's the same thing as the square root of negative 1 times the square root of b. But remember, the square root of negative 1 is just I. So I times the square root of b. So whenever you have the square root of negative b, you can just rewrite it as I square root of b. And again, here is the little proof of why that's true. So let's try this example, last example of today. So example 5, write the following in the form a plus bi. So again, they want us to write it in this nice form, and right now it looks a little messy. We can already see that there's a negative inside the radical, so we could apply some of these definitions. So we have 2 minus the square root of negative 12 over 2. So let's simplify this a little bit. So we have 2 minus, and remember the radical square root of negative 12 is the same thing as I radical 12 by this definition and by the little proof that I just did. But we do know that radical 12 has a perfect square. We know that 4 is in there. And so we have 2 minus I, and that simplifies to 2 radical 3 all over 2. So let me rewrite this. So we have 2 minus 2i square root of 3 all over 2. And remember, we wanted an a plus bi, so we wanted two separate ones, the real part and the imaginary part. So we have the real part is 2 over 2, and the imaginary part is negative 2 over 2, or 2 square root of 3 over 2, and then times I. So this simplifies here to 1 minus the square root of 3i. So here's my real part, here's my imaginary part. So now 2 minus the square root of 12 all over 2 is just simplified to 1 minus the square root of 3i. So again, sometimes you have the I in front of the radical or behind it. Just again, make sure that you can tell that it's not actually inside the radical. All right, everybody, thank you for sticking along.